Okay, so good afternoon, everyone. I'm Steve Morris. For those who don't know me, I'm part of the Vax-Hub in the UCL labs, normally in the Bernard Katz building, but unfortunately we still don't have access to our building, so we're all mostly in our homes still. So welcome to this second analytical webinar from the Vax-Hub, which for today we're going to focus on dynamic light scattering and nanoparticle tracking analysis. And this is going to have a presentation by Mike Kaszuba and Agnieszka Supa from Malvern Panalytical. Just a couple of housekeeping things to inform you of before we start. We're recording this webinar, hopefully so that we can then circulate it back to the various participants and ultimately, hopefully, by the Vax-Hub website for those people who can't attend for a wider audience. If anyone who wants to make a comment or raises a question or involves any discussion has any problems with that, that's fine. Please still go ahead, make your comments and engage in the discussion, and please let us know, preferably via Anne, you would like that part to be edited out of any sort of public version of this webinar. As regards comments during the webinar, you've got two processes. You could either raise your hand, and you've got the bar at the bottom, you've got a raise hand function, or you can simply type things into chat and we'll try and catch up with that. Those of you who are familiar with Teams will already know this, but some of you may not, is that the person who's sharing the screen and speaking can't actually often see the chat or the hand raising. So I think Anna and myself will try and sort of moderate that to raise the attention if people want to ask questions. So without further ado, let's move on into the webinar. So today we're going to talk about dynamic light scattering and nanoparticle tracking analysis. So these are two techniques which I'm sure many of you are familiar with already, but just as a little reminder, they are potentially ways of determining particle size and number of nanoparticles. So in the 0.01 to 1 micrometer diameter range, and they're potentially useful for a number of situations within vaccine development. So many vaccines now are essentially some form of nanoparticle, from just whole viruses through to VLPs, virus-like particles, through to gene delivery vectors such as the adenovirus systems. And all of those have a potential for development in the development process, the manufacturing process, and the formulation studies, to want to be able to make sure that the particles are the right size, the right structure, and the correct, you're not getting aggregation and degradation and so forth. So just here on the slide is this word DLS and nanoparticle tracking comes in. At the moment, within the Vax-Hub, within the Biochemical Engineering building at UCL, we have these particular instruments. We have a zeta sizer nano for determination of particle size and electrophoretic probabilities, zeta potentials. For NTA tracking analysis, we have the entry-level nanosite LM10 and the much more sophisticated nanosite NS300, which has the ability to do fluorescence-based measurement studies. In collaboration with Malvern Panalytical, they've generously offered, as part of the Vax-Hub COVID-19 work, the loan of their top-of-the-range model, Zeta Sizer Ultra, for evaluation and help in further development of our COVID-19 work. So just before I hand over to our two speakers, I'd just like to give you a little bit of background on them. So Agnieszka is a product manager at the Nano-Materials group at Malvern Panalytical. She's over 10 years experience we're working with Nanosite, providing NTA applications to internal and external customers, and collaborating research in a number of Horizon 2020 projects. In her current role, she is a customer voice within the product development and creates a vision and roadmap for the future of nanoparticle sizing solutions. Mike has originally a PhD from the Polytechnic of Wales, studying physical biochemistry of lipoproteins using NMR. He followed that with postdoctoral research into liposome drug delivery at the University of Manchester, and in '96 joined Malvern, which is now Malvern Panalytical, as product technician specialist for the Zetasizer range of instruments. And in 2010 was appointed technical support manager for the product technical specialist group in UK, France and Sweden. And is now, as part of that, providing technical support for users of various DLS and zeta potential instruments. So I'll hand over to Mike first, I think, for the actual presentation of the webinar.
Thank you very much, Steve. So let me just hopefully you can see that. I'm just going to get a laser pointer up here, so please bear with me. Okay. So as Steve said, my name is Mike Kaszuba. I primarily provide support for the Zetasizer product range. Today, I'm going to be talking about primarily the Ultra, the Zetasizer Ultra, which is this instrument pictured here on the left-hand side with the red badge. We've also got another one called the Pro, which has got slightly less capability than the Ultra. The Ultra is the top of the range. And really, this is a progression from the Nano. So those of you that have used the Zetasizer Nano will be familiar with performing size and zeta measurements in that. We've brought in new technologies and new enhancements into this instrument. And I think a couple of those are going to be very relevant to the work that you're involved with, particularly in determining particle concentration. That's generated a huge amount of interest for us since the products were launched. So I'm doing a joint webinar here with Agnieszka. The agenda, I'm going to do the first part. So we're going to talk about dynamic electrophoretic light scattering. Now, I'm aware that some of you probably have used DLS and ELS in the past. However, there may be people joining us that have not, and they don't know very much about the technique. So very briefly, I'll give a quick overview of that. I'll go on to talk about the Pro and Ultra, some of the things that we've brought into the system, which I think will be of interest to people here, and concentrate on three in particular, what we call adaptive correlation, multi-angle dynamic light scattering, or MADLs, and then an extension of MADLs is the particle concentration measurements, where we can get actual number of particles present per mil of sample. And I'll deal with some applications, and after that I'll pass over to Agnieszka, who will deal with the nano tracking analysis overview with applications as well. As Steve said, if anyone's got any questions, please either tap them into the chat capability or raise a hand. What I'll probably do is, as I switch over to Agnieszka, we'll just see if any questions have come in on my section, and then we'll revisit the questions at the end of the presentation as well. So let's start with DLS and ELS. So dynamic light scattering. What is it? It's a non-invasive technique. By that we mean we are not doing anything to the sample. The sample is contained in a suitable cuvette. We place the cuvette into the instrument, we perform the measurement, and the sample comes out in exactly the same condition as it went in. So it's completely non-invasive. We can measure the size of particles or molecules in suspension. The smallest thing we've measured in the instrument is sucrose molecules, which are 0.6 of a nanometer or 6 angstroms in diameter. So that's the capability we've got these days with modern technology. DLS is used in all sorts of applications for the control and optimization of processes, improving product quality and performance, for instance. What does it do? It actually analyzes the time dependence in the scattered light intensity. So when we pass our laser into our sample, the particles and molecules in that sample are undergoing Brownian motion, random movement. And that causes the intensity of the scattered light to fluctuate on at a certain rate. And what we are interested in is the rate of that intensity fluctuation, the time dependence in that intensity fluctuation. And the way we determine that is to autocorrelate the signal. Now, for this reason, some people know the technique as photon correlation spectroscopy. We tend to call it DLS now for the past 15 years or so, but ultimately it's the same technique at the end of the day. When we analyze this signal using autocorrelation, this allows us to get the hydrodynamic size from the measured diffusion coefficients. And a very important paper that was published on Brownian motion, I've referenced there, so Einstein's 1926 paper on the theory of Brownian movement. So in this little schematic, here is a sample contained in a cuvette. We pass our laser into that. The particles will scatter light at all angles. We are going to collect the light at a single angle. In this particular schematic, what we're looking at is 90 degrees to the laser beam, or we call that side scatter detection. And the detector we use is a single photon counting detector. We use avalanche photodiodes in our instruments, extremely sensitive, and it basically counts the number of photons detected as a function of time. Now, the important point to make here is that if we observe that scattered light over very long time scales, seconds or tens of seconds, we would see that the intensity doesn't fluctuate. It looks to be constant. What we are interested in is much quicker timescales. So we observe the scattering on nanosecond, microsecond timescales. And when we do that, we see it fluctuates over time. So typically what we get is an intensity trace in units of kilocounts per second or thousands of photons per second, plotted as a function of time. We pass that signal into an autocorrelator. And this correlator compares the signal with itself, separated by what we call delay times. So for example, if we look at the number of photons at the start of the measurement, then we look at the number of photons, let's say 100 nanoseconds further along, and then 200 nanoseconds further along, and all the way out to, in our case, 1.68 seconds. So we have a logarithmic spaced set of delay times in our correlator. And what we can see on the y-axis here is the correlation coefficient, or the similarity of the signal with respect to itself, plotted as a function of delay time. Now, for any random signal, and what we should be observing here is a random signal because we're looking at random diffusion processes. The loss in correlation of any random signal is an exponential process, and this is an exponential decay plotted on a logarithmic axis. This curve contains diffusion coefficients, and we apply suitable algorithms to that curve to pull out our distribution of diffusion coefficients, and then we convert that into our distribution of sizes using the Stokes-Einstein equation. Electrophoretic light scattering. So what is electrophoretic light scattering? It's a technique that measures the frequency shift of scattered light. So here we have a folded capillary cell. We call this a folded capillary cell. We have an electrode at either end. It's a U-shaped capillary cell. We place our sample in that. The sample is in contact with these electrodes. When we insert that into the instrument, we can apply a voltage, and then any charged particles or molecules in there will be attracted towards the oppositely charged electrode, i.e. they undergo electrophoresis. We pass our laser through the bottom of that cuvette. We observe the scattered light, and if that scattered light is arising from particles or molecules undergoing electrophoresis, it will have a frequency shift associated with it, or a Doppler shift associated with it. And again, for that reason, some people know this technique as laser Doppler electrophoresis. We tend to call it electrophoretic light scattering. what do we get out of that measurement? We get a parameter called zeta potential. What is it? It's a measure of the electrostatic repulsion that exists between the particles or the molecules that we've got in the sample. And as a consequence of that, it gives us an understanding of the stability of the system. Are those particles going to flocculate, or are they going to remain stable? Now, a very famous theory that was developed back in the 1940s, actually 80 years ago or so, two groups of scientists working independently, De Jager, Landau, Verwey, Overbeek. The theory became known as DLVO after the initials of their surnames. And what this theory says is that when we have particles and molecules in suspension, the stability of that system is going to be determined by the balance that exists between the repulsive forces, which are electrostatic in nature, and the attractive forces, which are van der Waals in nature. The zeta potential is a measure of the electrostatic repulsion. And you can calculate from theory that for an aqueous system, a general dividing line of stability is considered to be 30 millivolts. Zeta potential is measured in millivolts. So if we have particles which are more negative than minus 30, we have sufficient repulsion that it remains stable in this little diagram here. If we are below that, and the closer we get to zero, the less stable the sample will be. And the sample will undergo various processes. It could be flocculation, it could be aggregation. In emulsion systems, it could be creaming effects, for instance, or osville-ripening effects. So different processes can occur. So ideally, most people that we work with who are manufacturing products would like to have either a very negatively charged sample or a very positively charged sample, so that the product is stable for a long period of time. Now, the Pro and Ultra, very, very quickly. The Pro, I'm not going to spend too much time on this because I want to concentrate on three key things here. The Zetasizer Pro is effectively a Nano ZS, but a modern version of it. Completely new electronics, completely new software. So we have back and forward detection angles, as you've got in your Nano ZS. The software is completely new. We call that ZS Explorer software. Adaptive correlation, I'm going to spend a slide in a minute just talking about that, because we think it's a huge advancement in DLS, which is why we've applied for a patent. We've developed a neural network capability for sizing measurements. So what the software will do automatically, it takes the correlation function data and some of the key parameters we obtain from that measurement, and it will tell the user whether that data quality is good or bad. If it's bad, we will give advice as to the reasons why we consider it to be bad and what could be done to improve that. And also we give advice as to how those results, even if the data quality is poor, how they could be used. So that's kind of powerful. We've introduced constant current mode for zeta potential. That's new compared to nano. That's important if we're working in high salt concentrations. The nano, for instance, applies a constant voltage. And as a consequence, if we're working in high salt, we have polarization effects where ions are attracted towards optically charged electrodes. And that polarization causes an interference in the measurement itself. So what we've introduced in these instruments is constant current mode. So now the voltage will change to make sure that the current running in the system is constant. The optical filter wheel, two main things there. One is a fluorescence filter. So if we're trying to measure samples that we know are causing fluorescence in the wavelength of the laser we're operating at, we can put a narrowband filter in, which only allows scattered light of the wavelength of the laser to pass through into the detector. So that improves our signal to noise in fluorescent materials. And the other filters we've got on that wheel are polarizer filters. So if we are dealing with particles that are non-spherical or high aspect ratio particles, we may see a rotational component being detected. Remember that dynamic light scattering, we're looking at translational diffusion processes. Normally rotational diffusion, and all particles and all molecules spin, they rotate as well. But often they're on such rapid timescales that we don't see them on our correlator delay times. However, if we're dealing with high aspect ratios or actually things that we see this happen quite a lot in metal colloids like colloidal gold, colloidal silver, we see peaks appearing at very small sizes, which are due to the rotational component. And the polarizers in there allows us to differentiate the rotational component compared to the translational component. Now, the ultra, which is, we're in the process of arranging for an ultra to be loaned to you so that you can perform your particle concentration measurements, whatever you want to do. Apart from all of that, we've also got a third angle. So the ultra has got 3 detection angles, back, side, and forward. And what we are now doing is we are combining information obtained from those 3 angles into one measurement, and we call that multi-angle dynamic light scattering. And I'll talk about the benefits of what that gives you. An extension of that is particle concentration, and again, I'll go into a bit more detail of that shortly. Because we have the side scatter, we do have a low volume disposable capillary sizing cell, which allows us to make measurements of volumes down to 4 microliters. So that's that again, in certain applications, is very attractive. And because of that capillary cell, we have got an extended upper size limit. We've actually measured up to 10 microns in diameter in that cell. And this is because the capillary cell itself is very narrow, and the restricted dimensions of that cell minimizes the effect of sedimentation. So in a normal 1 milliliter sizing cuvette, we would struggle to measure anything above a few microns, but in this cuvette, we can go up to 10 microns. Now, I want to concentrate on these 3 because I think they're important and relevant to the work that you're involved with. So what's adaptive correlation? Well, quite frankly, it's a new way of making DLS measurements. In a nano, for those of you that have done DLS measurements in the zeta size of nano, you may be aware that we split the measurement into a series of 10-second subruns. And what we are looking at is the change in the mean count rate. So this is what we're trying to minimize is the influence of dust and contaminants on the measurement, because unfortunately, light scattering is extremely sensitive to the presence of large particles. There is a significant increase in scattering as you go up in size. So it may be that you've only got a few aggregates or dust particles present in your sample, but they can often dominate the intensity of the scattered light. So these schematics that we've always had in our software over the years, we're trying to minimize their influence on the measurement. So in the nano, we take 10-second subruns, and we combine a certain number of those subruns. Some subruns we throw away in the nano software. They've gone. We cannot recover them. They've gone. Now, in this adaptive correlation, we don't throw anything away. And instead of taking 10-second subruns, we're taking much shorter subruns, 1.68 seconds to be precise. And that specific time, 1.68 seconds, is defined actually by the architecture of our correlator. You might be wondering, why is it specifically 1.68? But it's defined by the architecture of the correlator. We look at the polydispersity index values of each of these subruns, and we statistically analyze them to identify which subruns are representative of the sample and which are not representative of the sample. In other words, what is the sample and what is the aggregate or the contaminant? And we categorize that into either steady state data, i.e. that is the sample, or transient events, i.e. that is dust or aggregates that are passing through the beam periodically. Now, we save both the steady state and the transient data. Okay, so nothing's thrown away in this case. Now, to give you an example, and I should say this adaptive correlation method, we require no prior knowledge of the sample. To give you an idea of that, Here we've got a sample, 1 mg per mil of lysozyme in a sodium acetate buffer, and that was measured on a zetasizer nano, and that's why we're calling it a legacy measurement, if you like. You can see the presence of quite a lot of aggregates in here, and the actual peak where the monomer is very variable as a consequence of that. It's just the influence of the presence of aggregates messing up the analysis of what actually we're interested in. Now, we take the same sample in the same cuvette, we run it in a zetasizer ultra, and this is what we get with adaptive correlation. It's quite astonishing, and until you've actually used one, people are very surprised by the quality of the data that we get out of an ultra compared to a nano. And don't get me wrong, the nano is still a great instrument, but we've tried to improve the quality of the data that we are accumulating in the measurement, because that ultimately will lead to better repeatability in the results that we get. Now, just to show you here, it's simpler sample preparation. It's much quicker than conventional measurements, 3 times quicker actually. In some cases, we can perform a DLS measurement in an ultra in less than 20 seconds, which is quite extraordinary. No requirement for user expertise. It's more repeatable. The results that we've generated, it's 3-fold improvement for easy samples. And we can also gain information on the aggregates. And the reason we can do that is because in the software, it allows us to either only look at the steady state data, or only the transient data, or then we can combine the whole lot together. Now you can see in this example here, the steady state data is the red line. The transient data, which only consists in this example of 1 or 2 of the subruns, you can see it's quite different to the steady state. And if we combine those 2 together, we have a big influence of those aggregates. But the beauty of this is we can look at the results separately. We can look at what is the sample, what is the aggregate. So it gives us a much better idea of what is contained in that sample. Now, MADLs. So when we are dealing with fairly large particles, and we can define those with diameters greater than 1/10 of the laser wavelength. So the laser used in the nano and the laser used in the ultra is 633 nanometers. It's a red laser. It's a helium neon laser. In the ultra, it's a 10 milliwatt laser, and I would suspect in your nano, it's a 4 milliwatt laser, so slightly more powerful in the ultra. If we're dealing with larger particles, the scattered light they produce is angular dependent, or what we call non-isotropic. So if we measured something much smaller, such as an AAV, that is an isotropic scatterer. The amount of light it scatters as a function of angle is exactly the same. However, if we get to these larger sizes, we get angular dependence. And here is an example. If you imagine we've got a particle at the center here and we shine our laser onto it, these are the theoretical plots that we would get for, in this case, polystyrene latex dispersed in water. We get a series of maxima and minima. You can see from this diagram that the bigger the particles become, the more light is scattered at the forward angle. In backscatter, we're actually less susceptible to the presence of aggregates because the amount of light that large particles scatter in the back angle is minimized. I should point out, by the way, that this is a logarithmic scale. So as we go through the angles, it becomes very much dominated in the forward angle. I've put in here backscatter, side scatter, forward scatter. These are the 3 detection angles we've got in the ultra. Now, as a practical example, if we had a sample containing quite a wide range of sizes, and some sizes in there are non-isotropically scattering, there might be aggregates, for instance, or something like that, and we look at the results we get at the 3 different angles, you can see that we get 3 different results for the same sample. Now, of course, this begs the question, well, which one of these is correct? And the answer to that question is, well, they're all correct. And it's always important that whenever you report sizes obtained by DLS, it's important to note what detection angle was used for the measurement, because If somebody goes to repeat the measurement and is using a different angle, then potentially you get a different result. In general, the more forward the angle becomes, the bigger the size you get. Okay, now what we've done with MADLs, we combine information, we combine the correlation function information obtained at the three angles into one. And we end up now with a unified angular independent distribution with increased resolution. Now, the reason it's increased resolution is we've now got information obtained at different angles. And this allows us to reduce the smoothing we apply in the analysis. And as a consequence of that, we increase the resolution. So if I just go back one slide, you can see here that at each angle, we're only getting a single peak. We don't see the bimodal. But if we combine the information from the different angles, we can now resolve those two peaks that are present in there. So that's a huge benefit. And what we've seen from the data that we've taken in MADLs measurements is that the resolution that we can achieve now in DLS is 2-to-1 size difference. Okay, now that will depend on various factors, but 2-to-1 in size difference. So for example, if I have one mode at 50 nanometers, I could resolve the second one at 100, twice the size. In a single angle measurement, we would be struggling to get 3-to-1 resolution. So we get increased resolution by using MADLs. Now we come on to particle concentration. So this is an extension of MADLs. So basically, we've done all the hard work in MADLs. We've combined the information obtained from the three angles. We've got an angular independent size distribution. And now we can extend the me theory that we've used to do it to obtain quantitative information. So it's an extension of MADLs. It's calibration free. We don't need to calibrate the measurement, but it works best below 0.5 micron, 500 nanometers. And the reason I say that is because if we go over that size, then the concentration of the sample that we need to prepare may not be appropriate for all angles. So, for example, we can work at high concentration in backscatter because we can work close to the wall of the cell to minimize multiple scattering. However, if the concentration is too high, we will get multiple scattering at the forward and possibly even the side angles. So this is why all the work that we've done on MADLs, really, it's only applicable for 500 nanometers or below. Of course, the good news is that viruses are less than 500 nanometers. So it works for all homogeneous sample types, i.e. not mixtures, but all the particles are the same. And it works over a relatively broad concentration range, which is size dependent, as you'll see in one of the slides. So what do we get from this measurement? We get the total particle concentration and also the concentration of each mode present in the sample. So here we've got the MADLs size distribution. You can see the main peak here. In this example is about 50 nanometers. We've got another very small peak. You can barely see it at about 100. And then another one about 0.5 micron. And you can see here we've got the distributed particle concentration information. So this main peak is at 10 to the 11 particles per mil. This second peak is 10 to the 7, and this one's even lower, about 10 to the 4, 5 times 10 to the 4, something like that. What do we need to provide the software in order to get this information out? We need to define the optical properties of the particles of the molecules we're measuring. So what do I mean by that? We mean the refractive index and the absorption of those particles. Most people would know these anyway. Anybody who's done DLS, if they're reporting their distributions either in volume or number base, rather than the basic intensity distribution, they would need to input the optical properties anyway. The dispersant RI and viscosity, well, they have to be put into the software even to do an ordinary DLS measurement. So that should be not a problem. And also the dispersant scattering intensity. Well, that's measurable. So what do I mean by that? If I've got particles in a particular dispersant, we need to measure the intensity of the scattering from the dispersant, because what we need to then know is what excess scattering those particles are producing. So to give you an idea, I've got here input parameters, the internal calculations that we do in the software, and then the output parameters. So input parameters, we take the total count rate from the sample. We've measured the dispersant count rate. Okay, so that is there as part of the measurement. And from that, we can calculate the count rate due to the particles themselves. We've already recorded the count rate from toluene. Now, you might ask, why do we use toluene? Toluene is used as a scattering standard because its Rayleigh ratio is known. So every instrument that we manufacture, and all instruments actually manufactured at Malvern, UK, toluene is measured as part of the production process. And the scattering intensity of toluene is recorded in the instrument's electronics. So the value is always there. Now, the reason we do that is there are going to be subtle differences in the sensitivities between instruments. So we need to, if you like, normalize that. So we measure toluene on every instrument that we produce. That value is stored. So that if then a user goes to do a particle concentration measurement, we've standardized the sensitivity of the instrument according to that toluene count rate. So we don't have to worry about that. We do the Madels measurement. That's done as part of the particle concentration measurements. We end up with our Madels particle size distribution, and then we've defined the optical properties of the particles and the dispersant, and that allows us to calculate the scattering cross-section per size class, and that in combination with the Madel size distribution allows us to perform the analysis. So we take all this information into the analysis, and we now get the total particle concentration, the distributed particle concentration, and the cumulated particle concentration. So that gives you a bit of background as to what goes on. That might seem very complicated, but the actual measurement itself is pretty trivial to perform. All of this is going on in the background, if you like. Now, this graph here shows that the concentration ranges that we can cover with this measurement in the ultra will depend on the material that we're measuring. So you've got here different concentration ranges for latex, for gold, and for protein. Okay, but for some cases we can get almost as high as 10 to the 20, and in some cases as low as just under 10 to the 8 particles per mil. Okay. This work was done in collaboration with the National Physics Laboratory, and it's really hot off the press, actually. This work has just been published, Journal of Nanoparticle Research. There's the reference. If anybody would like a copy of that, please let me know. We can. We've got open access to it, so you're welcome to have it. But it goes into a lot of detail about the precision and accuracy that we obtain from our particle concentration measurements. What NPL did as part of the study is to compare the values that we were getting from our instrument with the values that they were obtaining using other techniques. So it's a very interesting study, that. Now, applications. So hopefully that's given you a bit of a background as to what's going on in the ultra. I thought I'd start with something that I was fiddling around with before I joined Malvern, actually, liposomes. When I left Manchester University, I thought I would never see another liposome, but in reality, I've not stopped seeing them ever since. For 24 years, there seems to be an awful lot of groups around the world still working with liposomes. This is a classic study that people working with gene therapy applications get involved with. They're basically mixing DNA in plasmid form with liposomes, typically cationic because the DNA is negatively charged, and you form a complex. Blimey, when I was doing liposome work, this used to be called the meatballs and spaghetti model, actually. You'd have a meatball, i.e. the liposome, surrounded by DNA. So what's important here is the ratio of the DNA to the liposome, because that will influence the charge of the complex. You know, in some cases, you might have DNA surrounding a liposome, But in other cases, you might have the opposite. You might have liposomes surrounding DNA. So this is where zeta becomes very interesting. So here is a plot. Here we've got the molar ratio of plasmid to liposome. Here we've got the zeta potential. So when we have an excess of plasmid, the complex that's formed is negatively charged. We go through a particular ratio of plasmid to liposome where the complex is 0, it's neutral. And then when the liposomes become in excess, the complex becomes positively charged. So we can also look at the size of the complex. That's the beauty of a zeta sizer. We can do size and zeta in certain cells. And here we can see that the complex size, when the complex is either very negatively charged or very positively charged, is pretty constant around 90 to 100 nanometers. But as we approach neutrality, the complex size gets much larger. And this is because of aggregation. And now the van der Waals attractive forces are dominant. There's no repulsion present between these complexes. And that can have a big effect on transfection efficiency, of course. So what we can visualize here is that while the complex is negatively charged, we've got liposomes surrounded by DNA. But when we go to the other side of this, we've got a situation where the DNA might be surrounded by liposomes. Okay, so this information tells researchers that the ratio of plasmid to liposome they require to obtain a slightly positive complex. I mean, most applications, I guess, are looking for a slightly, well, certainly we were, to bind onto the surface of the mammalian cells we were interested in. We were trying to transfect cancer cells because the cells themselves are negatively charged. So the complex ideally needs to be slightly positive. This is another liposomal application. And the reason I like to show this is that I've come across over the years many people working with steric stabilization, so pegylation of liposomes, who often say, oh, but I'm using steric stabilization, so zeta potential is of no use to me because I'm not dealing with electrostatic repulsion. Well, that's not strictly true. And this is an example of where it's very useful information. So the stealth liposome, I think, was first reported in the 1980s by a lady called Teresa Allen from Canada. Stealth stands for sterically enhanced liposomal therapy, not the American bomber of the same name. But the stealth liposome, because it's pegylated, it dramatically increases circulation time in the body. So here we start off. We've got a plot here of the mole percent of pegylated lipid in the liposome, and then the zeta potential that's been measured. And we start off with a naked liposome. So we've made some anionic liposomes. In this case, they're about minus 43 millivolts in zeta potential. And we now start to put pegylated lipid into the liposome. And we can envisage a situation where around this value, we have partially coated that liposome. When we reach the plateau, we've saturated the liposome. So basically, we cannot physically fit any more PEG onto that surface. And what researchers use these measurements for is to determine what is the minimum concentration of PEG required to saturate the surface of the liposome. Now interestingly here, but one thing I said earlier about zeta potential and colloidal stability is that the more negative or the more positive charge we've got, the more stable it becomes. That's true if the mechanism is purely electrostatic. In this example, we have a steric mechanism. And here the opposite is true, because as we put more PEG onto the surface, we're increasing the steric stabilization of the particle, but we see a reduction in zeta. In other words, we become less negative and we tend to go towards zero. So we have to be careful how we interpret results depending on the mechanism of stabilization that we're using in our system. Now, we come on to some AAV work that we've done on Ultra. We've done a lot of work recently, actually, on AAVs. both internally, but also with lots of various companies who are working with AAVs. The first thing to show here, these are the size distributions we've obtained from MADLs. For full AAVs, these are our AAV5 samples, and also for empty. And you can see the empty ones not only are larger in size, but have also got higher polydispersity. And it's probable that this increase in size and polydispersity is due to the presence of oligomers. How can we prove that? Well, we've got the ability to go and use size exclusion because we sell size exclusion. But size exclusion allows us then to determine a separation technique, in other words, whether we have got aggregates present. And if we have got aggregates present, it can give us some quantitative information as well. You'll notice here that both full and empty here were about 10 to the 13 particles per mil in this case. On this one, what we're illustrating is how accurate the size is as a function of dilution of the AAV sample. So we're changing the concentration of that AAV quite significantly. The size ranges that we're getting are very consistent. So the open boxes you can see here, these are the empty AAVs, and the filled boxes, the slightly smaller sizes, are the full AAV samples. And across a quite wide range of concentrations here, we've got extremely good repeatability in our mean sizes. Coefficient of variation here is 5% in both cases. In this example, we're looking at the linearity and the concentration range. So we're looking at both filled and empty AAVs, and we're varying the concentrations. We're looking at how well the size remains constant, and we can see that's very, very consistent in terms of its size. And you can see the R² values in both cases are exceptionally high. The one where it becomes quite poor in terms of its linearity here are the lower concentrations. You see the CV here is 40%. This is because the scattering intensity that we're now detecting for such a low concentration is not that high, not that much higher than the background of the dispersant that the viruses are in. So your signal to noise now is being compromised, and as a consequence of that, we see lower coefficient of variation. We see higher percentage coefficient variation in this case. In this one, what we were interested in, because we determined particle concentration from Maddel's experiments, multi-angle DLS, we wanted to see, is there a benefit of doing this using multi-angle as opposed to doing it at a single angle? And you can see in all cases, at different concentrations, the Maddel's gives us higher precision in the concentration measurements that we've got. So now the final thing I want to just present before I hand over to Agnieszka here, this is work we've done with Allergan. We worked very closely with Allergan. In fact, when we were developing Ultra before launch, Allergan kindly agreed to do some testing because they were working with AAVs and they were very interested in viral titer. The first sample they measured was this ATCC reference sample. And what I've got here, the way they were doing the concentration measurements up to this point was capsidolysis. They still do, by the way. They're using the Ultra really as a complementary technique to the ELISA information that they get as well. What surprised them, because the capsidolysis technique gives them total concentration, they were not aware that this reference sample actually contained aggregates. And so what the Ultra told them was actually, the monomers, they are there at 1.1 times 10 to the 12, very comparable to what they were getting from their ELISA assay. But it also, the ultra measurements also gave them concentration information and the presence of these aggregates. The other measurements in here are actually AAV samples from Allergan themselves. And in this case, again, very good consistency between what we obtained with the ultra and what they were getting from their ELISAs. And this one was beautiful, in fact. You can see they've got quite a variation from 2 repeat measurements in the ELISAs for this particular sample. And again, we're still very much in the same ballpark of 10 to the 12. So the particle concentration measurement here, we're typically talking 2 to 3 minutes per measurement. It's a very rapid measurement. And it allows us to not just get the total concentration that we've got, but if we resolve other modes in that distribution, it gives us the concentration information from those modes as well. So just so that you're aware, we hold a series of webinars throughout the whole year. I mean, I can't remember how many there are this year, probably, I don't know, approaching 100 or something. And they are recorded. So even if you can't make the actual date and time that they're being held on, you've got access to listen to them in your own time. And I just wanted to focus on this one. This one was given by Kirsty McManus from Allergan, where she discussed how they use the ultra in their workflow for AAV development. So if you go to our website and you search for this particular title, you'll be able to listen to that webinar. There are also other webinars on particle concentration. A colleague of ours, Hannah Yankovic-Jones, has actually done 2 in the last fortnight discussing specifically AAVs and how the precision and accuracy of the measurements that we can obtain using an ultra, discussing that. So those are also in there. For anyone to access this on our website, you simply have to register your contact details, and then you can download or watch anything you want. So if you're not registered on the website, we strongly recommend you do that. I've heard a lot of academics over the years tell me that our website is possibly one of the best resources for certainly light scattering information of anyone on the web. In many respects, the whole DLS technique originated in Malvern in the 1960s, 1970s. So I guess we think we know what we're talking about when it comes to light scattering. So there's an awful lot of information there available for you. So anyway, on that point, I shall stop sharing my screen, which will allow Agnieszka to hopefully pick it up from that point. While we're waiting for that, has anyone got any questions on the information that I've gone through?
Hello, hi, this is Adil from Oxford. I was wondering if I could ask a quick question.
Yeah, sure. Just
a very quick. So, I mean, I've used DLS in the past, and I guess it sort of gives you, with the old nanosizer, it gives you sort of this broad, if you've got, heterogeneity in your sample, it gives you sort of this average which kind of spreads, and I'm just wondering, based on what you've said, would you say that the ultra could give better resolution in?
Yes, certainly we've seen that. And just very briefly, why does DLS tend to give broad distributions? The correlation function, which I mentioned at the start there, that ultimately is what we obtain in a measurement. We obtain a correlation function, and we have to analyze that correlation function to get our size distribution information out of it. Now, let's imagine we start with a scenario that I've produced a sample which consists of only one size, right? Now, nobody on planet Earth can do that. The closest you can get to one size is a polystyrene latex standard, but even that has got a certain number of different sizes of particles in there. But if we could, the correlation function would contain one exponential decay rate, and it'd be very easy to analyze that. As we go up in polydispersity, we have more and more decay rates. And now it becomes mathematically more challenging to try and extrapolate all the different decay rates and hence the different sizes that we've got in there. The advantage of MADLs is that not only is the decay rate dependent on the size of the particle, it's also dependent on the detection angle. So now we've got more information to work with, because not only can we look at the decay rates as a function of size, but we can look at the decay rates as a function of angle. And that increases the resolution capability of the technique. So what would be interesting in the example that you just mentioned, if on a Zetasizer Nano you're getting a fairly broad monomodal peak, if you did the same measurement using MADLs, it may well be that you resolve other modes because of that extra information. So,
thanks a lot, Mike. That's really useful. Just one quick question on PDI. Person and refractive index.
Yeah.
Do you have if I was to make up a new buffer with various excipients, you know, these new cocktail, how's the best way to sort of input that information?
Well, even with biological buffers, what we find is that even if there are various excipients in there, the concentrations that are in there are typically not going to influence the refractive index of the base solvent, if you like. So I'm assuming these are going to be aqueous based. So even if we're working in quite complex buffers, most people would use the refractive index of water. Okay. Now ultimately, if we have any concerns that the presence of these excipients will influence refractive index, honestly, a handheld refractometer, a couple of £100, you put a drop on it and it will measure the refractive index for you. But I suspect it's going to come out at the same value as water, or very, very close to it.
Thanks, Mike. Okay, I'll shut it down.
Okay, if there are no more questions, we've got another opportunity at the end as well. I'll pass those to Agnieszka.
Okay. Thank you very much, Mike. Great introduction to DLS and very detailed talk, so thank you for that. I hope you can all see my screen now.
Yeah, it's good. Yeah.
Thank you for confirmation. So I'm going to introduce you to another Malvern Panalytical product range that can often be found alongside with the Zetasizer instrument in many labs. Same, I think, is also with you. So you also, along Zetasizer, you have actually two our instruments, so LM10 and NS300. The NS300 system, our flagship instrument, is actually presented on the slide currently on the photo. So I'm going to give you some highlights of the techniques in the first instance, as I appreciate some of you might not be so familiar with it. So nanosite, really what it does, it provides you with really high resolution particle size distribution, as well as it gives you the particle count. It's often used for checking the effectiveness of your purification or isolation processes, or looking at the control aggregation of your sample, checking whether your sample contains any aggregation. And the instruments are capable of doing this for biological particles, from as small as around 35 nanometers. The systems has optional mode of measuring detecting the fluorescence signal. And really the measurements are quite easy and quick. There is a minimal sample preparation similarly to Zetasizer. On the top of that, what you get, you really get a visual confirmation with your moving particles that I'm going to show you in a second. So I think similarly to Zetasizer DLS technique, Nanosite also is using the laser to illuminate our sample. The sample we measure is always a liquid suspension, and we're really measuring the nanoparticles suspended in that liquid. So similarly to DLS, nanoparticles will move in that suspension under random Brownian motions and will scatter the laser light. This light, the scatter light, will be collected through our optical setup and go to our digital camera. So this, I hope, is playing now and you can see it. This is a typical image that you're obtaining from your nanosite system. So what you're actually seeing at the moment, you're seeing the points of scatter light that comes from the particles moving under Brownian motions. So that's our visual confirmation. Just a note here that the particles we see they're not directly seen by the camera. They're too small to be seen by the camera. But what we're seeing here, there are points of scatter light that are detected by the camera and they're moving by Brownian motions. So contrary to DLS, we won't measure the direct intensity of this light scatter. What we will do instead, we will follow the movement of those particles. So in the bottom, we've got like example of the particle track. So you can see this is a very random motion. And when we follow that particles, we can determine the diffusion coefficient. And that's, again, using the same equation, the same principle as DLS, we will use the Stoke-Einstein equation to calculate our hydrodynamic diameter. So for this, we only require to know the temperature and viscosity. And because our systems are usually used with aqueous solutions, this is quite well known and automatically, applied in the software for water-based samples. So because we're not looking at we're not measure the intensity of the light scatter, we're looking at the speed and measuring the speed of those particles. We actually don't require the information about the refractive properties of your particles. So we don't need this as DLS. So what then we do with that image? Obviously, we rely on the software. The nanosite gave beginning to nanoparticle tracking analysis technology, and our software utilizes this approach. So the image you've seen previously, is coming to the software. Then all of the white dots here that you see are assumed to be particles. In the first step, we identify each individual particle. The next step, software applying various algorithms will follow every single particle individually and all particles simultaneously. So we'll track our particles. So we call it tracking. And that will result really with really high resolution particle size distribution. So as I mentioned, because we do particle by particle tracking rather than looking at the bulk mass of the particles, we are able to distinguish, very small population within a sample. So in this example, we're looking at the mixture of 100, 200, 300, and 400 nanometer latex. So you can see all of populations can be nicely seen in our size distribution. So for size, we also meet the particle tracking analysis, so-called PTA, ISO 9430 standards. And we also, as I said, are able to measure particle concentration. So with the image you've seen before, you can see the individual dots. That means that, knowing the volume those particles are dispersing, and that volume is calculated by the software, we can very easily count our particles. And the graph here shows really that nanosite operating in and show very linear dilution for concentrations up to low 10 to the 9 particles per mil. And the graph on the right-hand side shows how reproducible our concentrations measurements are on various sizes of, in this example, latex, so from 60 nanometer to 300 nanometer, where 6 or 7 individual labs were performing measurements of the same sample. So you can see how reproducibility measurements across the labs. So where are we operating and what are the limits of our system and technology? We really can detect particles as small as 10 nanometers. However, this really depends on the sample properties, material type. So highly scattering materials like metals, so gold, silver, the system will be able to detect from as small as 10 nanometers. This also might depend on the system configuration. So the more sensitive camera, the shorter the wavelength, we might be able to characterize the smaller sizes better. For biological particles, where they're not scattering the light so well as metals, the lower size limits starts around 30-35 nanometers. The upper limit of detection for size is really dependent on the Brownian motion. So around 1 micron size, those motion disappear or gets very limited. And for us to be able to follow it and follow this movement and record the movement, this starting to be very challenging. So around micron size is the top what we can measure. Obviously, again, this is dependent on the sample characteristic and the solvents they disperse with. For example, the viscosity can, change the movement of particles, the same the temperature in which we measure these particles. For the concentration, so our systems, because of the field of view in which you're observing your particles, for the ideal measurements, we really want to have the particles to have around surroundings to move freely. So it's quite important that we observe about 30 to 100 of these, dots, particles in a screen. And that results that our concentration measurements are performing best when we're talking about samples diluted to 10 to the 7, 10 to the 9 particles per mil. So what you find in most of the biological samples is that you really have to apply dilution to your sample. Most cases, this dilution does not overcome more than 100,000 times, but that's something to be aware. So in a really high concentrations, the software will still will be willing to analyze your sample. However, as you can imagine, the image will be crowded with the white dots. The particles will be crossing their paths. So for the software, it will be really hard to follow all individual particles. For the lower end, when we're only seeing 1 or 2 particles on screen, even if we apply the flow for a better statistic, this still might require much longer analysis time and result in quite poor statistic. So now I'm really going to move to the applications. And I just wanted to say that Nanosite finds its application in many sample types, from pigments and paints to really biological applications. A little bit from the history. So the Nanosite and NTA technology has started in 2002, when its founder and inventor Dr. Bob Carr, after a year's working with viruses down in Portendown, really wanted to see the Brownian motions of viruses and really wanted to get the measurements of viruses in minutes. So although the Nanosite products have been initially used more in industrial applications, including oils, with time, Nanosite's got its popularity also in virus applications. So today I thought I will really show you, how we evolved with the time and how we've seen the Nanosite to be applied to many virus and vaccine VLPs applications. So just wanted to start with a very simple picture where we be looking at how simply Nanosite is used to compare 2 different types of the same virus. So we look here at human cytomegalovirus, when one of the groups in Institute of Virology in Berlin focuses on viral immune invasion mechanisms of human herpes viruses and was interested to study the viability and virus structure. So the group was comparing the wild type as well as the mutants with deleted MHC1 downregulating genes. And what we see that in very quick analysis, 2 types were compared for its size distribution that really remains the same for both the wild type and the mutant. But what is really clearly seen here that the mutant contains twice many particles. As I mentioned, the nanocytes product have been used for many years to assist the virus characterization. And one of those processes is obviously assisting the virus purification, while the monitoring the level of impurities in production processes is critical in order to stop production runs as early as possible when the problem is detected. So as early as 2012, the Kramberger evaluated the nanocyte for the total virus particle determination, and it's used the ability to quantify latex particles, adenovirus 5 and influenza virus during a couple of days of measurements. In this example here, the data from that investigation is showed for the influenza virus. And you can see the change in the size distributions and mode size. So after purification, the size distribution is much narrower, and the model size, is much smaller. So, regarding the same topic for the purification, the Cardiff group has incorporated nanocyte NS300 system in the gene therapy adenovirus characterization. So firstly, the system was used to check the purity of the sample and the effectiveness of the isolation and purification process. So I'm sure you're all aware that the adenovirus is around 100 nanometers, and any impurities and purification, any impurities after purification process can be easily observed in nanocyte distribution as additional populations peaks in the size distribution. So in here, the primary mode, around 90 to 100 nanometers was obtained, and a couple of small shoulders are seen here, which are assumed to be a contaminants from the purification process. So moving on to showing you example of really well purified virus, how it might look. So this is example where we're showing, the work from Matizzi group that developed a novel, safe and stable Ebola virus reference material by encapsulating the Ebola virus antisense RNA into HIV-1-like particles. So the lentivirus particles are replication deficient and not infections due to the lack of HIV-1 genes and envelope protein. And Ebola virus genes were subcloned and for encapsulation into 2 lentivirus preparations. To confirm the correctly shaped particles were produced with the system, the supernatant was analyzed using the nanoparticle tracking analysis, which determined the average particle size of around 101 nanometers, and with expected concentration range of around 3 times 10 to the 10 particles per mil. The same preparation was also visualized by electron microscopy and showing the spherical particles with evidence of internal core structure and average diameter around 115 nanometers. So that was consistent with that of the wild type HIV. So such measurement was really to ensure the sample was stable and free of contaminants. And yeah, as I said, I really wanted to point out the really nice monodispersity of that distribution. So another group also worked with lentivirus. So Oxford Biomedica was developing several gene therapies that utilize its equine infectious anemia virus-based vector platform technology. And detailed characterization of lentivirus vector particles was critical to ensure the quality and consistency of batches, and also for manufacturing development purposes. Again, nanoparticle tracking analysis was used to analyze lentiviral particles with comparisons to data obtained with flow cytometry and RNA copy number analysis. So consistent model of 100 to 200 nanometer were seen in analyzed samples, and particle concentration really increased through the manufacturing process optimization, and was similar to reported to RNA particle number estimations. So Information about the aggregation state is also important for further use of the viral suspensions. It's well known that the storage of virus preparation leads to aggregation of virus particles. The effect of storage on the aggregation state of virins of EMCV virus was analyzed using two methods, so NTA and TM. Aggregation of freshly isolated samples stored at 4 degrees for 2 weeks was demonstrated by NTA, while TM hasn't really shown a significant change in the viral morphology. And the measurements with NTA really show a distinct change due to aggregation. And that really highlights the need of utilizing many characterization technique for your sample characterization. So also recently, the World Health Organization has set some guidelines on evaluation of vaccine stability and recommends to conduct basic and accelerated stability studies to determine optimal stabilizing conditions and establish the shelf life specifications. So in this example, the RABV samples used as colloidal particle model were incubated in the temperatures ranging from 5 to 60 degrees. And the results presented here are shown from the 30-day study. The unstressed control was stored at -70 degrees. And during the study, many techniques were used to analyze the samples that will include NTA, ELISA, the ddPCR, DSF, and DLS. As you can see, the force degradation induced a significant changes in physical properties of viral particles. That can be seen in increased average particle hydrodynamic diameter with increased temperature that was observed by DLS. That really confirms the presence of larger aggregates. The percentile diameter ratio, so-called Hill span, was used to express the polydispersity of particle size distribution by NTA. And again, I've lost my cursor, indicated the increased particle size with incubation temperatures over 37 degrees. Additionally, increase in particle polydispersity under thermal stress over time was accompanied by continuous loss of G protein antigenicity measured by ELISA and NTA. So those results really demonstrate that NTA can be applied on virus-based solutions to simultaneously count antigenic viral particles and determine aggregation states of various particles. In this example here, I would like to show you how the virus-like particles would look like. So this is a typical video from virus-like particles in a size range around 140 nanometers, and typical distribution from virus-like particles. NTA obviously can easily measure the size and concentration of virus-like particles, as well as it's quite interesting that many other biological assays might struggle with it, why the virus-like particles don't contain any infectious or nucleic acids inside. So as I mentioned in the very, very beginning, nanocyte can also detect the fluorescence signal. So if you ever have sample that express fluorescence properties, or you incorporate attached fluorophore to your virus-like particles, under the light scatter, the system will be able to collect the both signals, and you will get your measurements as you would normally do with nanocyte. However, if you want to look specifically on the mixture of particles or your population of particles that were targeted with a specific fluorophore, you can apply the fluorescence filter, and that what will happen, the laser light scatter will be blocked, and the only signal that will come through and will be collected by the system will be a fluorescence signal. So this was again done and used by the Cardiff group. So obviously adenovirus structure and its composition is very well known. But the fluorescent labeling with quantum dots was performed to confirm really the presence of the hexane proteins on a adenovirus capsid as well as a knob region. So to target the hexane protein in the virus capsid, anti-hexane biotinylated antibody was used, and next it was linked with the streptavidin quantum dots. Obviously, sample then was diluted and measured with 405 nanometer excitation, and the fluorescent signal was collected with 430 long pass filter. Adenovirus also has 36 knobs, so that gives us in theory 36 potential binding sites. So to target these regions with streptavidin linked quantum dots, biotinylating kit for AVTAC was used. So by use of appropriate vector, AVTACs were generated on the knob protein and next biotinylated. Next, similarly to the hexane protein, we've linked it with the streptavidin quantum dots and analyzed our samples in both the light scatter and fluorescence mode. And as you see on the both slides, where the purple line is the light scatter, the orange is the fluorescence, you can see that we successfully targeted both sides, both hexane proteins and the knob region, and successfully analyzed both samples in the light scatter and fluorescence mode. The group studied the potential of the fluorescence capabilities with nanocyte further. So the purified adenovirus was then labeled with DNA dye, cyber gold, and characterized again in the light scatter and fluorescence mode. I will try to play those videos for you. This preliminary data show a good efficiency of around 70% of virus population detected under fluorescence mode. That confirms the presence of the DNA inside of those virus particles. The labeling obviously needs a further optimization. However, it proves that NTA has a potential to determine the ratio of empty and full viruses. And one more example. So we've been challenged again in a Cardiff group to come and help them with the characterization of the cytomegalovirus. This virus was challenging as the titer of this virus after infections was very low, so they struggled really to apply any characterization techniques. However, they had a method for purification that was based on glycerol titrate gradient, which was able to remove the NIPS and dense bodies and all the cellular contaminations. So this allowed to separate the virus from the NIPS, so non-infectious particles, for those that don't know. As you can see, the bands of NIPS is nearly invisible, but very skilled user managed to actually extract the two bands from this. And we've put it on nanosite, and as you can see, we clearly see the two fractions analyzed. As expected, the NIPS fractions was in much lower concentration. We actually didn't have to even dilute it for nanosite. We applied very small 5 times dilution, and both samples were analyzed successfully. And really to finish off, I'm sure you all are interested how the technique compares when you analyzing the same sample with biological assays. So the Anderson in this paper really compared the plug assay and the qPCR for assays and analyzing the phages. So the graphs here show the comparison of qPCR with plug assay, nanosite with plug assay, and nanosite with qPCR. The diagonal lines are representing the perfect agreement. What you can notice is the nanosite usually reports much or slightly higher virus titer than the both biological assays. And this is similar to DLS, the same what Mike really said for DLS. Remember that both DLS and nanosite NTA techniques count the particles, the total number of particles. So we will be counting Those they are full, those they contain some nucleic acids that are infectious, non-infectious, as well as many contaminants that might be detected in a sample. So that will include the cell debris, samples, impurities. And that was really my last slide. So I will stop sharing and hand over, I believe, to Steve for questions.
Okay. Thank you very much, both of you, for that. So it's very informative. So we still have some questions. And Kumar has put something into the chat. So for the characterization of 40 kilodalton lipidated protein, which has a tendency to aggregate, which instrument would you suggest? And would the same apply for formulation containing aluminium adjuvants?
Sorry, I would just say if it's a 40 kilodalton protein, it's a pretty small protein. It's only going to be a few nanometers. And I correct me if I'm wrong, Agnieszka, but I don't think that's an NTA application. I think that's more a DLS one. Yeah, I mean, we do a lot of protein work on DLS. Because we've got built-in temperature control, we can also do thermal ramps. You know, a lot of people do thermal ramps to look at aggregation temperatures and things like that, or denaturation temperatures. So, I mean, 40 kilodaltons, top of my head, I'd say would give a hydrodynamic radius of about 2.5 to 3 nanometers, something like that. So, I mean, that's certainly not within NTA size range, I don't think. So certainly DLS, I think, would come into that.
So nanosite is also used for, you know, characterization of many protein aggregates. However, as Mike said, the same limit of detection will apply as to biological particles. So we won't be able to see the protein monomers or dimers, trimers. Nanosite really comes into the play for those aggregates from 30 nanometers. So if you are interested in early stage aggregation detection, DLS potentially is the sweet spot for that. If you're looking at, you know, what really at high resolution, at understanding, you know, what happens after this primary aggregation has been formed, potentially combination of the two might give you the full picture, because DLS will be again much more sensitive to those aggregates, even above 1 micron size, while NTA will give you the picture between 30 and micron size that might be missed from DLS. So I think after, you know, this initial aggregation, the two techniques gives really the full picture.
Okay, thanks. Sandy Douglas, you have a question or comment you'd like to make?
Hi there. Yeah, two quick questions, if I'm allowed. First one is, how do each of these techniques cope with the presence of detergent micelles?
In terms of DLS, that will depend on the size of the micelle and how close that is with respect to whatever you're interested in measuring in that sample. So, for example, you know, if you had viruses in there, 30, 40 nanometers in diameter, and you had micelles, it's all about the relative intensities at the end of the day. The refractive, so if we're dealing with proteins, the refractive index of a protein is going to be similar to the refractive index of a micelle. So now it comes down to the relative sizes of each of the species that you're interested in, the relative concentrations of those species that are in there as well. So I've come across over the years situations where micelles are present, which are very similar in size to in that case, the protein molecule that they were interested in detecting. And we can't differentiate, therefore, the scattering of one compared to the scattering of the other.
How about with viruses?
Viruses are slightly bigger. They would scatter more light, I would think, than the micelles do. But again, you know, it comes down to the relative concentrations of each ones that are there. If the micelles are there just above CMC, they're probably not going to contribute that much scattering to the overall intensity, and we probably wouldn't see them in the presence of the viruses. So it's not a simple answer, because what you've got to think about, at the end of the day, we simply detect photons of scattered light. So you've got to think about everything that could influence the intensity of that scattered light. So you're talking size, you're talking concentration, you're talking optical properties.
Okay.
Similar thing will be with nanocytes. So usually the micelles, because of the size, will be below our limit of detection. However, it can happen that if they're in a really high concentration and the particles we're talking about are quite small, it can have some interference. But in general, the particles, even biological particles, usually scatter more light than new micelles.
Oh, yep. Somebody has their hand up there. Adel. Adel, you're on mute. Yeah.
Hi, sorry, thanks, Steve. So I'm interested to know more about the fluorescence mode in the NTA, and sort of whether it's possible to look at more than one label at a time in a sample, or is it pretty much, one-off? Could you, for example, do a nucleic acid stain and say another antibody against a surface protein?
You could. So we offer 4 laser wavelength excitations, and obviously with each we offer standard long pass filters, and those filters can be customized as well. However, you have to be quite smart. So ideally, to differentiate the signal, you would have to potentially excite your nucleic acid with 1 wavelength and detect it with 1 filter, and then have enough stock shift difference between your protein label to make sure that you're collecting that signal only from your protein tag. So, for example, if you detect your nucleic acid stain with above 500 nanometers, and then you detect your proteins above 650, I think that would be possible. But you have to be very smart with your wavelength to not overlap. Or you could do pretty much, the same sample, put it into 2 different, lasers, and that would give you that distinction as well. So it's possible. It's not the easiest way to do it. We don't have a simple switch in the software, but it's not impossible. We've recently also been quite successful with analyzing the thread signal. So if you're interested in things like that, we're happy to discuss this further.
Thank you very much.
Any more? No. Just check me. There's nothing else in the chat. No, just thank yous. Okay. Well, I guess if there's no more, we are technically at the end of our slot. Thank you, guys. That was really good.
No, pleasure. Thanks for the opportunity.